We recover the key from a known plaintext ciphertext pair. Okay, suppose you are an attacker and you know one particular message, say M, that has been encrypted, and you got the corresponding ciphertext. Okay, the question is, can you recover the encryption key from that particular known plaintext ciphertext pair? Remember, the same key is used for many plaintext encryption. So it would be a disaster if you could recover a key from one particular known plaintext ciphertext pair. But I wanted to investigate what does it take to recover the key from a known plaintext ciphertext pair. Okay, very quickly, Feistel network we have discussed in other segments, but I will summarize very quickly for you. So remember, the Feistel network is basically you have a block. Let's say the block has 6 bits, just for example. In practice, it's not 6 bits, of course, it's much bigger than that. In the case of DES, it's 64-bit block cipher. But I'm going to focus only on the smaller example to just get the core idea across. Okay, so I'm assuming the block cipher length is 6. Okay, that means you have 3 bits to the left, 3 bits to the right here. Okay, let's call this M0 made of 3 bits, M1 made of another 3 bits. Okay, what is the construction in the Feistel network? The construction works as follows. M1 gets copied as it is to the next round. Okay, what we do with the M0 is that we send it to an XOR block, right? We take M1, we send it to another block here, pseudorender function, let me call it FK, right? And FK produces some output, some random gibberish, and that goes as an input to the XOR. So XOR needs 2 inputs, right? One is the M0, another is the FK of M1, and that produces some gibberish as well because of XOR property. So the output of XOR will now come here to the next round. So this will become your M1, this will become your M2, okay? And now, let's say one more round. What we will do is, again, we will have the same FK, same K. Actually, it's not the same K, to be more precise. It's multiple Ks. There's one round key K1, second round will have another key K2. It will be bad to use the same key, okay? And of course, internally, these keys are derived. From outside, you have only one key K, and K1, K2, and so on are derived from that key using key derivation algorithm. Okay, so what are we going to do now in the next round? Remember, this gets copied as it is, so your M2 will come here as it is. But we will also send this to a pseudorender function, which will produce some gibberish, and that we XOR it with the M1, right? And that comes out to be another gibberish, and that becomes our M3. So let's say we stop here to only 2 rounds. This is not secure, but let's say we stop here for a moment. Okay, let's think about from an attacker's perspective, right? What are they seeing? Let's say they know M is made of M0 and M1 for a moment. They know the ciphertext also, right? Because it's not secret anymore. Okay, so given the ciphertext, this is the ciphertext because we stop at the end, this ciphertext. Given M and the ciphertext, can we recover keys K1 and K2? Okay, if we are able to extract that key K1 and K2, then we can break cryptography essentially. We can observe any ciphertext and reverse engineer the plaintext because we know the key. So what is it stopping anyone to do that? Okay, so as you can guess, most likely the novelty should be in how FK1 and FK2 works. The function FK actually works, okay, pseudorender function. So in the previous segment, I talked about some properties. One of the important properties is nonlinearity, okay? So that's an important property we will leverage. So let me create a simple F in this discussion, okay? I'm going to assume a 6-bit block cipher, right, for a moment. Okay, so I'm going to define my F as follows. F, remember, takes a key and another block. Let's say this is 3-bit and this is 3-bit, right? What is the output of F is also 3-bit. So let me define F as follows. Okay, Y3. Suppose I define my pseudorender function as follows. Okay, I say this is nothing but, remember it has to give me 3-bit output. It takes 3-bit input and gives me 3-bit output that we can XOR it with the other part, right? So it must be a 3-bit. That means there must be 3 components. So I define a nonlinear relation like this, x1 times x2. These are individual bits, x1, x2 are bits either 0 or 1, right? x1, x2, y1, y2. So I'm mixing my key and the message, so to speak. And the second component is, say, x2, y3, or x3, it doesn't matter. Some nonlinear relation I'm plugging in. And then x1 plus x2, okay, times y1, y3, okay. I want to summarize what I'm doing here. I'm designing this function f, okay. Remember, f takes 2 inputs. One is some key, another is some data. Okay, so 3-bit is coming, and 3-bit is coming as input, 3 bits is coming out as an output. That's basically what I'm doing here, okay? And we are assuming K1, K2 are also 3 bits, okay? So there are 3 components here. This is first component, this is second component, this is third component, okay? So if we have a function like this, and let's take an example message now and walk through what happens if you know a plain text and a corresponding ciphertext, how you can reverse engineer. Can you reverse engineer the keys K1 and K2? What does it really take? Let me take my key K1. Remember, I need 2 keys in this case because I'm just doing only 2 rounds. Okay, that means I need 6 bits, right? So what if I create my key K1 to be made of K2, K4. These are individual bits. It can be 0 or 1, okay? K6. And the key K2 to be, this is, don't confuse this K2 with this one. This is small k, this is capital K. Second key that I will be using is K1, individual bits, K1, right? K2, K7, okay? Whatever you're seeing within the parentheses are just zeros and ones, okay? Basically, that's all, okay? So now let's apply Feistel network on a piece of known plain text, okay? Okay, how are we going to do that part? Let me finish one more thing. Let me define the message. My message, let's say my message is 1, 0, 1, 1, 1, 1, okay? So you can imagine here I have 1, 0, 1, right? That's basically the meaning. And here I have 1, 1, 1. All right. So what is the, how do we define M2 now? Okay, M2 is subjoined by, let's define M2 now. How do we define M2? M2 is subjoined by, okay, this is M0, just to be clear, and this is M1. Okay, we can now easily define M2 as follows. M2 is nothing but, we have to take M0, XOR it with FK of 1, input M1. So we need to do those 2 things, okay? Which means we take M0, okay, XOR means plus modulo 2 arithmetic, okay? F is the function that we have, which we need to send key K1 and M1, okay? We know what key K1 is, right? Key 1 is made of 3 bits, K2, K4, K6. Of course, the attacker has no idea about these bits, otherwise the whole thing is broken right away. We want to find those keys, of course. That's where I'm going. Which means if you plug into this formula that I wrote for the definition of F, you will get M2 to be made of 3 components. What are the components? M2 is made of components 1 plus K2, K4. That's the first component. I'm just plugging in the formula, okay? And then K4, K6, the formula for function f was defined already up, okay? K4, K6, these are small k's, individual bits, K4, K6, and 1 plus K2, K4, okay? Just coming straight from the formula, okay? Very quickly, let me explain at least one component of this formula. I say here 1 plus K2, K4. The reason is as follows, right? I'm taking f of K1, M1, right? What is K1? K1 is K2, K4, K6. and the M1 is 111. Okay, so all of the bits here are 111. So 1 into 1 is 1. This is modular arithmetic, by the way. Okay, and here x1 plus x2. Okay, what is x1 plus x2? X1 means K2, x2 means K4. Okay, and we do add and then do a mod 2. So the answer is always within 0, either 0 or 1. Okay, that's basically M2. And if we continue like this, we will do now for M3. So M3 requires, what is the logic for M3? M3 requires us to do the same. We need to do M1, right? We have to XOR it with f of K2 M2. Okay. And we know the formula for F again. And we know what K2 in general, the structure of K2. We don't know the actual values of K2. We don't know the 3 bits, right? And we will have another equation, which is, if you simplify this, we get 1 plus K2 K4. Okay. And let me clear this. It's not K2 K4, sorry. It is much complicated. 1 plus K1 K2. I'm going to only write a few segments. This is a long formula. 1 plus K1 K2 times 1 plus K2 K4 times K4 K6. This is the first component. Okay. And I will leave as a homework to you to complete the remaining 2 components. Okay. So you have to have another component here, another component here. So you need these 2 components to be filled. So you have M3. Okay. And imagine now, if you have multiple rounds, you will have lots of equations like this. Okay. Let me call this as equation 0 because this is the function F. The first equation we got was applying M0 f of x, K1 and M1. Okay, this is the first equation, and this is the second equation. So every round gives you 1 equation. Okay, so if you do T rounds, you'll have T equations. Okay, remember the last round will give you the actual ciphertext that you see on the wire. Okay, you don't really know the intermediate outputs, of course. Otherwise, you will be able to easily break, relatively easy to break if you know the intermediate outputs. Because you have to just do an XOR operation to get everywhere. Okay. All right. So what is that I'm going to tell you now? So let's say I'm stopping here. Okay. So I did only 2 rounds with you, and I'm stopping here. So what is the resulting equation that we need to solve as an attacker? Okay. And, so I'm going to use a notation C. So remember, this is 3-bit here, and this is 3-bit here, right? That means we are seeing 6 bits on the wire. Let's call those 6 bits as a capital C made of 6 bits, C1, C2, C3, and so on until C6, right? Okay. So we know these values for C1, C2, C3, C4, C6. These are individual bits that we see. So what is the, excuse me. So what is the first equation we'll have? Remember, I said this is C1, C2, C3 here, right? This is what I'm seeing on the wire, 6 bits. And this is C4, C5, C6. These are individual bits. We know the input M, we know the output ciphertext. We are trying to reverse engineer K1, K2 in this case. So what is the algebraic equation we have? We have this nice equation. C6, the 6th component, is nothing but a set of equations, I must say. K1, K2, individual bit C1 is 1 plus K2, K4. Okay, so what you're seeing is basically a bunch of equations. All these equations are coming from Feistel network definition. Okay, just from the network, we are able to derive this. Okay, so what are the things we know? We know C1, C2, C3, C4, C6, C5, C6. These are published as part of the ciphertext, the final round. And we also know the initial input, otherwise we wouldn't have gotten this equation. Okay, what we don't know is K1, K2, K3, K4, and so on. We don't know the individual keys, of course. So that's what we wanted to find out. So we have an equation. We have a set of equations, C1 to C6. We know these values. These are the values that we know. So we reduced the problem of breaking Feistel network into a problem of solving a bunch of nonlinear polynomials. Okay, I say nonlinear because you can see here I'm multiplying two variables. Okay, that's the reason. Of course, everything is in mod 2. Multiplication, addition, everything is in mod 2. Okay, so just with 2 rounds, we get this equation. Imagine a scenario where we have to go through 4 rounds, okay, 8 rounds or more. And imagine a scenario where you have the number of keys is like, let's say in this case, I have key size extremely small, right? My key K1 is just 3-bit. In practice, you would have very, very large key size. So you are going to have set of equations like these, right? Maybe you will have, say, in the case of DES, you'll have 64 equations, right? Because you have 64 bits for each block. So you're going to have 64 equations made of so many unknown variables, right? Every round has its own key, right? Key K1, K2, and so on. They're all made of 64 bits. So you're going to have gigantic number of equations and unknown variables. So it is considered NP hard problem in theory of computation. What it means is that we don't know a polynomial time algorithm to solve this equation. Okay, when I say this equation, I mean this set of equations that you're seeing. If there is a polynomial algorithm to solve this, it's not only going to break this Feistel network construction, but solves many other hard computational problems. Okay, so I'm not going to talk a lot about NP hard, but informally I'm saying that there doesn't exist a polynomial time algorithm as of now. Okay, so but if somebody gives you a solution, K1, K2, K3, K4, the individual bits, you can easily plug in and check whether the solution is correct. That's the reason why it's called the NP problem. And it is also considered NP hard. Okay, so if you solve this problem, you're solving a lot of other problems. That's an amazing fact about the theory of computation. Anyway, so you now understand, hopefully, that the underlying computational problem behind the Feistel network is this solving this set of equations. And these equations are not easy to solve.